What?
Oh, I slept like 2 or 3 hours. Almost slept through the meeting. That was dangerous.
Why did you not get so much sleep?
I was putting together my presentation.
Whew.
Oh,
How are you?
yeah, me too.
Huh?
Yeah,
Yeah.
good. How about you?
Oh, dragon. What did you answer?
Champions.
Oh, I thought he said Trabian. I was saying Trabian.
3 good.
Yeah, I was like,
So, how many meetings do we have? just one.
no, we have,
I think we have 4.
next
including
week,
today.
Tuesday, Thursday, and then the next 2, so 4.
Okay. One of those is already.
So if we, well, labs is, as always, our free will initiative. But the formal meetings at the lecture time, I think we do today, twice next week, and once following week. And after that, I'll probably show up here in the room just in case anyone wants to chat informally. But as soon as you do presentations, you're free. So how do we organize this remaining four meetings? So we need to complete a review of time-dependent density function theory, and I will spend maybe complete meeting today and half of the meeting next time. Coming Tuesday, we will finish time-dependent density function theory in the same format as we finish all theories that we covered in class. So we will draw a flowchart. And I'm not sure if you will have time to make quiz or not, because the semester is coming to the end. But it will be like conversion of ideas of time-dependent density function theory into algorithmic way to see how does it work in practice. The length of the course doesn't allow to go into all derivations, but probably you do not consider it very tragic for the theory. So we'll cover main ideas. And next, well, this Thanksgiving weekend, or maybe a little below, a little after, is the main time to complete calculations for research project. So it is desired, assumed, expected, wished that by the time we meet in 1 week, each of us will have sufficient amount of computational data to convert from research activity to scientific communication activity, which also takes effort. So last week, we will have one more lab to tie the loose ends, but let's plan on completing as much as possible right now. Well, in a week from now on. And as you have probably experienced, it takes a little less time than wet lab work. So mostly you just submit jobs in time and then you wait until they are completed. I will be in the material modeling studio today at 5 and tomorrow at 5. You need to come just once. So there will be very few of new material. Basically, it will be an opportunity for one-to-one communications for catching up your research projects. I may show a little of the analysis of orbitals for identifying charge transfer states, but it will be really brief. And I would like to introduce you to those who will be able to visit. I will make a brief introduction to the superpower, to the National Energy Resource Computing System, NERSC supercomputer that I have an ability to open like little accounts for you, and if you are tired of the university computer and think it is not sufficiently productive, you have access to something a little quicker. So that there will be guarantee that in the remaining week you complete everything that you want to complete. So that you can't complain that resources were not sufficient, therefore here is my geometry, that's it. Okay. When we were discussing the formulation of your research projects, there were some one-to-one discussions, and there are specifics for each project. For those who are not sure about specifics, there are some projects that are relatively general. There is a very oversimplified protocol. Take the ground state optimized geometry, change electronic configurations, compare their density of states and spectra, run very high temperature molecular dynamics, take new geometry and explore properties after this heating. Sometimes it leads to completion of some reactions, sometimes it just changes the properties, like it very often closes the gap and makes it to absorb in the infrared, but it is just last resort if you do not know what to do. For most of you, you have an idea how to process with your projects. If you're looking into reactions and your reaction is not going in the direction you want, one of the opportunities is to explore the reaction in the different, for us, we can tell with different total number of electrons, with different oxidation state. But you can convert it onto the language of practical wet chemistry, like changing the pH, acidity, or whether it is reducing or oxidizing environment. If it is reducing environment, it means that it is an excess of electrons. If it is oxidizing, it is a lack of electrons. And you can model this environment by changing total number of electrons. Sometimes, if you modify it, reactions drastically change their how they develop. Another way to look on it is to see that if your substrate, if your model contains something solid, is connected to bias, to electrode, which is connected to either positive or negative of the better. So there are some ways to analyze change of total number of electrons and look into the reactions. Yes, please.
Is there a way to modify the isotope that we're looking at instead of using hydrogen, use deuterium, for instance?
Yes.
Okay.
Look into the podcasts.
Okay.
And there should be an available potential for changed mass.
You have to change all the masses then? Or just one?
No, just one. You take the podcar for, instead of podcar for hydrogen, you take podcar for deuterium.
Okay.
So that's so it's a separate.
Yes,
file.
yes. It will be named instead of H. Yeah. And if it is not available, you can just make a copy of the podcar for hydrogen to your local directory. Do not spoil those centralized. and find line where it determines the mass.
And then in the pass car, do you have to change then the H2D as well, or do
Well,
stay the same?
it doesn't matter how it well. It is for your comfort to see
I
that
see.
it
I suppose.
appears
Never
with
mind.
letter.
Okay. Yeah,
You can call instead of like hydrogen and deuterium, you can call them potatoes and apples. The program will run the same way.
yeah. Okay.
But if you only want to change one, you have to remake your
Exactly.
postcard.
Yep.
Right, that's right. There are two additional skills that we didn't cover in labs, but maybe we can postpone it to our last lab meeting. The normal mode analysis and actually running the TDDFT, which is very simple. It goes along with our previous experience with Gaussian, just changing one line in the input and making sufficiently small system and having sufficiently large amount of resources. I am going to distribute something. So hopefully it's not a fire alarm. So I am wishing you relaxing and pleasant Thanksgiving weekend. But maybe you feel bored. And right now, there are no obligatory homeworks at all. This is just to your entertainment. There are two things that are obligatory, mandatory. Those are presentations in 2 weeks from now and written reports, which will be due in a week and 2 days from now, but you may start thinking on them. And the homework is formulated in such a way that you develop your written reports step by step. But some intellectually gifted individuals, without irony, have a talent to do everything in the last hour. If you consider yourself in this category, you don't care about splitting responsibility over several days. This is just a little guidance that you can take and consider, but judge your own abilities and resources, and I don't care how you get to the point. So this is optional homework that covers introduces some ideas on thinking a little bit on the time-dependent density functional theory, which just listening what we will be discussing today. And most of you do not have TDDFT components in your research, so it is just entertainment or investment into the future. Then there is a little guidance of what to do with how to navigate your research if you do not have any ideas. But I think most of you have very clear, what to do. And then you can start composing your reports. Even if you do not have results by now, you may formulate a little paragraph or half page, whatever, depending on your mood, telling what is the challenge that you want to address and what is your hypothetical resolution of this challenge. Like, why did you decide to do this research? What is unknown and what you want to compute in order to resolve it. And then as time goes, it will go pretty quickly, we will fill those Word documents with a couple of figures and tables, and then a description of what we see and how we conclude. So final written report will be very short, something that anyone can complete. If materials, results available, anyone can complete in maybe an hour. But you may start thinking ahead so that you have less hectic in the last night before it is due. Another handout for your entertainment that the one I distributed has some value. You may invest time in looking through it. Other two are completely entertaining. If I would be not offended if you put it under the back cover of your notebook and forget about it, or use it as kindling for your fireplace. So first one is 6 pages from the book by Rich Martin on the time-dependent density functional theory. It doesn't, this brief overview doesn't include the rigorous derivation, but it gives the overall context of connection of TDDFT to regular DFT. And some of you may consider TDDFT as a primary tool of your research for several years. So this is more in the style of good research paper with main statements and comparison on practical examples at the end. And some of you who are interested in silicon quantum dots may appreciate it most. Do not look to exact data because this is a copy from a book which is not super obsolete, but it is not this year. So they have not the up-to-date functional, they are good just with main trends. Another last handout for today is the example of what independent research projects in course like this may result into. So this is trace of how one of the attendees of such class processed. So it was a project in class, a little seed report, and then in about a couple of months from them it was growing, adding a little more details, and then it converted into research paper. But it was the first author has experimental background. He never considered himself as a theorist or computational expert, but it's just teasing you and showing that there is some possible continuation of your research projects if you are if they are going well. And you do recognize some figures that we did as the homework, at least the style of the figures, where the anions and cations are compared. Okay. So just in case if you just woke up, or if I have just woke up, we are in the computational chemistry for 76/676, meeting number 26. We are looking on to density functional theory, and our last meeting will be on Tuesday, December 6th, 2 weeks from now, where hopefully everyone will be enthusiastic to make some presentations based on the individual research projects. In case you do not remember what your project, which is very unlikely, and would be a little too late to set up right now, So we do have studies of calcite, of the electronic properties of metalloporphyrins, the reactions catalyzed by metalloporphyrins, the reactions catalyzed by metal surface for the diaphragm. Then we have two research projects about carbon nanotubes, chemical etching and use of carbon nanotubes for sensors. And there are another set of projects for the metal semiconductor interface and metal clusters, and two research areas for very closely related to dye-sensitized solar cells. Electron transfer at the interface of semiconductor and organic dye. So we are finishing the fourth chapter of the course dealing with time-dependent density functional theory. We have 4 meetings more today, next Tuesday, coming Thursday, and then a Tuesday 2 weeks from now. And we are continuing going over time-dependent density functional theory. When we met last time, we did cover a comparison between orbital picture and excitonic picture. And we did set up a framework to deal with excited state theories. We formulated an order, a request, what we as users need from those theories. So any theory, any method for excited states should provide a set of transition energies and oscillator strengths that for users we can use it as a black box and we can say no matter how, but with a little curiosity we are looking on the way how those two types of parameters are computed. So the primary difference between our approach, our approximate approach that we use in our practical component of the course by now, in non-interacting orbital approach to absorption, we are formulating transition dipoles and oscillator strengths on the language of pairs of orbitals. If we are going to the time-dependent density functional theory, these two primary characteristics, transition energies and oscillator strengths, are formulated on the language of the density, so-called transition density. And the main question, it's like a half-minute derivation, but main question is how to get transition dipole out of transition density. So if we get an answer to this question, then we are free to go. I'm just looking for time. And meanwhile, there will be some more or less useful things. So the answer will be on the last slide, and this panel will progress as we go slide by slide. Before we go to the sweet spot that we really need, I will make a couple of comments that may be of a little curiosity or value for your research projects. Please give me a secret sign if, like little hand waving, if this picture doesn't bring any memories in you. Okay, then give me an open sign if this picture gives you some memories. Okay. So when we are playing with evaluating the electronic structure of our materials, we do not take into account quantized vibrations, and we never will in this course, because the course ends soon. And it is a frequent mistake to forget about nuclear reorganization, which is very okay for solids, for dielectrics, for oxides, but it is very not okay for soft molecules. And this image summarizes this idea, so that if we are looking onto optical properties of a material, then we should take into account then upon perturbation by light, the material, the molecule can experience substantial change in the geometry. So what we are typically exploring, we are considering, so here the all geometry of a molecule is projected just on one coordinate, and what we are exploring is this blue line. So we are looking on transitions between electronic states for geometry corresponding to neutral ground optimized state. But if we need to estimate ability of a molecule to emit light, then it is frequently needed to evaluate the geometry that the molecule takes upon photoexcitation. So in our oversimplified methodology, in our oversimplified modeling, it would mean to set up the Fermi weight key in the VASP and let it optimize. So then it will bring to the position that corresponds to excited state. Same for anions, cations, and magnetic states. As zeroth order approximation, we can keep unchanged geometry and explore different electronic configurations. But typically, if you tweak something with the electronic configuration, it will change the geometry, it will reconfigure. And if one wants to be more precise, it could be reasonable to optimize upon any change of the configuration. Since we are limited in time, one can do exploration only at the ground state geometry, but just properly label it and tell that one may anticipate that geometry will change further if one optimizes. Because some of the systems are big, and even if today we will get an access to supercomputers, still 1 week is not a very long time. How does one quantitatively explores this difference? Well, one can look for excitation energy from, let's say, HOMO to LUMO in the ground state, and then the HOMO to LUMO gap at the geometry corresponding to excited state, and their difference of this red and blue line will be what spectroscopists call Stokes shift. So primarily goal of this is nuclear reconfiguration. So one may estimate the value of this Stokes shift for the models that we treat. Also, there is a comment that I always wanted to give but may have forgotten. The difference of orbitals energies is the lowest possible ladder step in the precision. If we are limited in the resources and we cannot go to advanced theories, but we want to increase precision a little bit, then the much more preferred way to get trustable energies is to compute total energies only. So instead of looking on the orbital transition, you create necessary electronic configuration, like excited, anionic, cationic, and then you compute the difference of total energy for the changed configuration and ground state configuration. This results turn to coincide with experiment much better. And you may, if you're curious, you may explore how the orbital energy difference compares with difference in total energies. Okay. And if you are exposed to spectroscopy of organic dyes, you know that absorption and emission spectra may differ substantially because of this nuclear reconfiguration. And this is not an organic dye, it's something different. But this is general feature that is observed in many materials. And also in spectroscopy of organic molecules, one often see the vibrational progression that we will not get in the method that we are doing right now, because our nuclei are not quantized. So if you know for sure that there are progression, we will see only 0-0 transition in what we are doing right now. If one critically needs this vibronic progression, then one needs a little different methods. They are available, but not in this limited time frame. So before we get to our sweet point, here's a little scattered comments, but they can be valuable for your research. So some of you have identified your interests as being related to charge transfer. And we all can characterize our model by finding Kohn-Sham orbitals, which are building blocks for total density. They are not highly trustable things. They are just basis to compute something real. But substantial insight and understanding of the systems can be obtained by analyzing spatial distributions of orbitals. Each orbital takes a lot of space on the disk. Each orbital takes a little exhausting effort of humans to draw. Even if you use some scripts, just looking on it. If you have a relatively big system and you have a couple of hundreds orbitals, you just watching them one after another, you need to sleep or take a coffee and have some rest. So, but sometimes we need to identify if the model exhibit properties for charge transfer. Sometimes one looks on the pairs of lowest excitation home orbital if they are localized in different spatial areas of space. And if they do, one tells, good, it's photoinduced charge transfer, good for photocatalysis, good for photovoltaics, whatever. But many systems have lowest transition neutral without charge transfer, although they are able to exhibit useful charge transfer properties for the higher excitations. So one may need to screen more than one excitation to find charge transfer states. And there are several ways to do it. One is to compute not transition, but regular dipole for each orbital and see where the center of this charge distribution is, whether it is coincide with center of mass of molecule or it is shifted. One way. Another is to project the three-dimensional charge density on one selected axis. And then this three-dimensional picture will convert into one-dimensional, and one probably can plot all hundreds orbitals at once and just see whether there are heroes among them that do not follow the general trend and have maxima in specific, in some exotic regions of space. So it's just integrating this three-dimensional charge distribution over X and Y, and we will quickly do it when we meet in the lab. So this could be interesting to those who are interested in charge transfer. So like if we have special distribution in one area, one can integrate and over x and y and see that in z it has peak here. If it is distributed in different area, it can be integrated and see that it is in different area. So pairs of orbitals with different localization of charge.
Question.
Yes, please.
Those do you sum along the z-axis?
No, you sum along x and y, and you keep z untouched. So it was like taking a slice where z equals constant and adding together all values of densities.
But then what does that give you?
Dependence on z. If you have big inhomogeneity along x and y, it is not the best. But if you know for sure that your model is aligned along z-axis, this can give additional degree of freedom for good analysis. One thing that we are not covering because of lack of time is so-called partial density of states, the distribution of orbitals over atomic orbitals, which is not a bad skill, and we can cover it individually after the course ends, maybe on the last informal meeting. Okay, so here is the summary. It is last slide that we had on the blackboard before we left, right? Something like this. So if we need transition dipole, we compute it as the expectation value of the position operator between pair of Kohn-Sham orbitals. And it is not a scalar, it is a vector consisting of 3 components. So if you need the square of transition dipole, we need each of them squared. And it is typically used as an input for oscillator strengths, and it is assumes the isotropic distribution of all molecules, or isotropic distribution of observers. Like there is one molecule and a million of scientists who look from different angles. Probably an ensemble of molecules is easier to imagine. So here are the constants that we all were looking for. And it's a little challenge to memorize. So it has the oscillator strength is proportional to the square of transition dipole and the energy of transition frequency. The rest are elementary constants: mass of electron, charge of electron, and Planck constant. And if we are doing things in atomic system of units, then those become 1 and the equation becomes simpler. So the pi cancels and it becomes the only significant factors are transition dipole square and transition energy. So by plugging in a couple of elementary constants, one can get from the dimensionless transition oscillator strengths to the Einstein coefficients of spontaneous emission and induced absorption and induced emission, A and B coefficients. So they are also formulated in terms of transition dipole and oscillator strengths. So if we need to estimate the excited state lifetime, then we take inverse of oscillator strengths, wrap it up with few more elementary constants and the transition energy squared, and then we get to the lifetime. So there is a version of the code for transition dipole in our repository that we use that adds additional column in the oscillator strength file and reports the lifetime in picoseconds or nanoseconds. So for each transition between each pair of orbitals, we have a quick way to estimate lifetime of excited states. Why excited states do not live eternally? Where energy is going to? Why it is dissipated? Although we are skipping derivations, but what is the basic answer? Like, why? Huh?
Thermal fluctuation.
Fluctuations of what?
Ions.
If we suppose a hypothetical universe where ions are absolutely frozen, with no vibrations of ions, would the excited state live eternally, or it will have finite lifetime?
Perturbation is longer.
Perturbation by nuclear vibrations is no longer,
right.
but nuclear vibrations are nuclear degrees of freedom, and they would be responsible for non-radiative lifetime, for non-emissive transitions. But here, emission, it means that electronic degrees of freedom interact with what? There is no trap. If we had only molecule, excited molecule, and then after it emits, we have a ground state molecule and, yeah, quantum of light. And light, what is light? Yes. What is light if inside your laser? It's just a simpler question. If you do have a laser, which means like two mirrors and some junk between. It's propagating, but there is a standing wave of electromagnetic field. And this standing wave has different amplitudes. And even if we are at 0 Kelvin, even if ions are not moving, the electromagnetic degrees of freedom have 0 oscillation. Same as in harmonic oscillator, the ground state has 1/2 h nu. And interaction of electronic degrees of freedom with this ground state oscillations of electromagnetic field are responsible for spontaneous emission. So even if our ions are nailed for freezed completely, there will be spontaneous emission. And we can compute it. Precise or not precise, it's a second question. But we can estimate and qualitatively say that, okay, this pair of states, this excitation will be long-living, and this one will quickly go away.
So that's assuming that you have additional perturbation after you are in the excited state.
The 0 oscillations of electromagnetic field are always existing around us. We are not alone. Electromagnetic waves follow us. And they exert a perturbation on electronic degrees of freedom that lead to spontaneous emission if they are thinking that they are too good to be excited. So everything will dump sooner or later. Good. So we do have width in our equations for absorption spectra that take into account non-zero vibrations, some vibrations of nuclear degrees of freedom that we describe by Gaussian functions. We do have oscillator strengths, and we do have transition energy as difference between elementary pairs of orbitals in our old style, in the orbital picture. When we go to the excited state, excitonic picture, we will have these two pairs of data, this kinds of data set computed from different types of equations. Okay, we already covered this. Total energy in one geometry and another geometry helps. So where the time-dependent density function theory comes from? It comes from the fact that ground state molecule is perturbed by light, which in our dipole approximation, which we discussed last time, can be approximated as oscillating electric field. There is a distribution in space, there is a magnetic component, but they are negligible if you are looking on objects of the order of 1 nanometer. So if we do have oscillating electric field applied to charge density, to cloud of electrons, to the charge, electric field applied to charge makes charge to move. And if it is moves as a whole, then we have a plasmonic mechanism of excitation. So all charge density moves inside the system with the frequency determined by light. This is good for macroscopic or like nanoscale plus systems of several of 100 nanometers. If you're looking on the molecular size, there is, instead of continuous energies, there are discrete energies. And instead of moving of the electron density as a whole, as all together, the exertion of electric field promotes transitions between orbitals. So we are looking on the response of our electronic system to perturbation by periodic electric field, right? So no one objects. Probably it's time to go to the blackboard. So originally we have density of electrons and we have all terms in energy that we can formulate as Hamiltonian that are self-consistently satisfy each other. But now we are modifying our Hamiltonian by additional terms, H prime, which can be our original Hamiltonian minus interaction with electric field in the dipole approximation. No, you can keep your feet. No, well, I'll use this one. Keep your feet on. I'm not a fan. So, suppose I'm electric field. I have a frequency of maybe 1 revolution per second. Then I apply it to the molecule. What will be the frequency of the revolution of everything that is connected to it?
It will be 1.
Yes.
But it will have a phase factor, probably.
Phase factor, but it will be same frequency.
Yes.
If the perturbation has specific frequency, then the response to perturbation will have the same frequency. If you have sudden, if I come and kick it, then there will be all frequencies. But if I'm persistently for infinitely long time perturbed at the same frequency, then everything will come into quasi-stationary state when everything will be changing with the same frequency. So we can assume, very logical, there is no big gap, that our density will start depending on time, and it will have the amplitude of vibrations and the time-dependent factor. So the density will get time-dependent contribution. So it will change with time. At the same frequency as the inducing factor. resonance. So if, how do you call this device?
Swing.
Swing. So if you try to increase the amplitude of oscillations on a swing, you need to, and you are a swinger, you need to apply perturbation with some specific frequency. If you start moving more frequently or less frequently, you will get no big amplitude motion. So the response of system to perturbation is maximal at resonance frequency. Okay? Goes along with common sense. So here is amplitude of the response. So we are probing our electronic system by perturbation at different frequency. And we are exploring at which frequency the amplitude of this response will be maximized. So basically, we put inducing frequency as the x-axis argument and the amplitude of the response as y. And then we can make experiment in our minds, Gedanken experiment, when we are changing frequency and see at this frequency there is response, and this there is, and this there is not. And we need to find frequencies, omega 1, omega 2, omega 3, at which response is maximal, and we may want to find the values of this response, rho 1, rho 2, rho 3, at that correspond to the perturbation at given frequency. Objections? Whew. Then you know what time-dependent density function theory is. The rest are just boring mathematical details. So it is a response system, a response theory. Response of electronic system to optical perturbation. So how is it formulated practically? So the increment of total energy, if you perturb with given frequency by quantum laws, will be h bar omega, and then we are looking for the amplitude of the response. And this response, this change in density due to transitions, would be logical to call transition density. So we are looking for transition density as function of omega. So a little summary what we discussed right now and what we started in our previous meeting. So we do have modified Hamiltonian, perturbed Hamiltonian. We do have modified density. And I would like to write something on the blackboard. Just one, maybe one equation. So one can find several orders of perturbation. Those first order will be linear in the intensity of amplitude of electric field. The second one will be quadratic in the electric field. And one can go further. But at the small amplitude of perturbation, we do not need to go higher than the first order. When we are going to the first order of perturbation theory, we are allowed to change only one of the modify only one of the orbitals, either one or another one. If we are going to the second order, then we can perturb both orbitals. And the message is that if we are staying within first order of perturbation theory, we do not have simultaneous change of both orbitals. Therefore, we do not affect the segment of the density matrix that corresponds to occupations. So the density matrix is composed of 4 segments, one for occupied, one for unoccupied, and 2 for cross terms. In the ground state, we have ones here on the diagonal, zeros here on the off diagonal. If we are in the second order of perturbation theory, we will be able to modify occupations. But if we are staying within the first order of perturbation theory, we have modification only of these off-diagonal terms. If you want more details, it would take several hours of derivation. I'm trying to condense it. So, in the first order perturbation, only of diagonal parts of density matrix are perturbed. So let's call these blocks of density matrix X and Y. You can call anything by any name you like. And then we know that the diagonal parts will not change, but this off-diagonal change will experience some change. So the main question of time-dependent density functional theory is to see response of this X and Y, of the off-diagonal parts of the density matrix to the periodic perturbation. Response of the off-diagonal terms in density matrix into periodic perturbation. And as you have seen in the little diagram on the on the lower part of our blackboard, those amplitudes, they are not time dependent. Time dependence is gone because we know that all oscillations will go on with the same frequency as an inducing factor. So we need only the amplitudes which are frequency dependent, not time dependent. So from now on, we forget about time dependence, and we have time dependence only in the name of the theory. Okay? So we need this x and y. And then we go from orbital picture to excitonic picture that we discussed prior. So there is equation derived by scientist with last name Cassida that formulate this problem on the language of eigenvalue problem. So those x and y are off-diagonal parts of density matrix, and they are written as a vectors. You can matrix is set of numbers, and you can just take them one by one and write into the vector. So you take this x and y, write them into a vector, formulate the appropriate superoperator, and set it up as an eigenvalue equation for transition energy. So this will be an equation that will have solutions only at those frequencies omega 1, omega 2, omega 3, when the system exhibits maximal response to external perturbation. The frequencies correspond to where this response is, and the x and y are amplitudes of this response. It may sound, you may observe a little lack of logic because it's not a complete story. One derives these equations continuously with Fourier transform and with perturbation theory, but for our purposes, we just skimming through equation for the x and y. What are these elements of the superoperator? If the Cassida equation gives answers as a transition energies, then in the zeroth order, those superoperator is just diagonal with energy difference, orbital energy difference. And if you remove everything else, the Cassida equation will produce results in the orbital picture. What are additional terms? Same as in all our quantum chemistry approaches. There is a Coulomb term, and there is a exchange and correlation from density functional. But since we are looking not on the ground state density by transition, it is a second order of the total energy exchange correlation component in response to the variation of density. So second functional derivative. So if someone asks you what is a super operator in Cassida equation, you can briefly answer it as second functional derivative of total energy in respect to density. So the diagonal blocks are not affected and off-diagonal blocks are affected. So if we solve Cassida equation, which is implemented in many codes, then we will get frequencies and we will have values of the density matrix elements for this off-diagonal terms, transition density matrix. So the last question, and I think today will be the only time when plan matches the allowed time. So what if we do have density and we do have operator? How to find expectation value of the transition dipole? So what are we doing? We need set of transition energies and we need set of oscillator strengths. But now we formulate everything in terms of density. How to find expectation value if we do not have wave function, if we have only density or density matrix? to simplify, and make a simplest possible example, I am considering only transition between HOMO and LUMO. Then our all transition density matrix will be represented by one element here, one element there. And then we do have matrix elements of the transition dipole mode. Typically, it is 0 for transition from HOMO to HOMO and LUMO to LUMO. And we are taking, let's say, only X component, although it is a vector. So, in case we do have operator and density, the procedure to find expectation value is formulated as multiply these two matrices and take trace of those, right? So here is the matrix of transition dipole moments, which means that we have found expectation values for transition between each individual orbital. And here are the density matrix elements that, in this specific case, come out from TDDFT calculations. Now I am going to practice row by column multiplication. So row by column. And to skip all these indices, I will write only D capital. So 0 times row HOMO, row by column, plus D times row LUMO HOMO. This is X, this is Y. Here, 0 times row HOMO LUMO plus T times row LUMO LUMO. No errors yet?
I don't think so.
Next, row by column. T times row HOMO HOMO plus 0 times row LUMO HOMO. And the last one. This row by this column. T times row LUMO HOMO, which is Y in our transition density matrix. Row.
No, that should be
No,
HOMO LUMO.
Okay,
HOMO
HOMO
LUMO. And LUMO LUMO.
plus 0 times row LUMO LUMO. So the trace means that we forget whatever was on the diagonal and we take sum of the diagonal elements. D times row LUMO HOMO plus D row HOMO LUMO. So one was X, another was Y. So matrix element of transition, X plus Y. Right now, our matrices are reduced just to one element because we are looking for one transition. If we are looking for more rich spectrum we will have blue. But you see that as soon as we do have elements of transition density matrix, we do have a procedure to compute expectation values of transition dipole element. So from transition density matrix, we are getting transition dipole moment expectation value. And then we can use it to find oscillator strengths. Oscillator strengths. Make sense? I think it is same as here. So we didn't fail on the board by multiplying matrices 2 by 2. So it is a procedure to get observables out of density rather than orbitals. Okay, we are finishing maybe a couple of minutes below time. But so when we were working in the orbital representation, our absorption spectra were collection of resonances at the offsets of energy between initial and final orbital with amplitudes coming from oscillator strengths that also computed from orbitals. When we are in the excitonic picture, we again have a set of resonances where these transition energies come from the poles, from solutions of Cassida equation, and the oscillator strengths come from expectation values of transition dipole computed with transition density matrix. So time-dependent density functional theory is another tool to compute absorption spectra, considered more reliable and of higher precision. Guess what will be on the next slide? Okay, well, can I expect someone to come today? So if you plan to, especially if you plan to travel to Thanksgiving holiday, then consider coming today. If you staying in Fargo, well, I will be coming twice. Just wait, I will wait, whatever, 20 minutes. If no one shows up, I will go and relax. If someone shows, you'll go forward. Meeting is dismissed. Let's. You are free to go.